up. You've been asleep for months. You have videos to be making. Wake up! Okay, obviously considering the subject matter of this video, I must declare that this video is intended for educational purposes. I'm not going to be held. I won't be held responsible if you decide to do some shit and get yourself arrested. Always get permission from the person you're targeting to run exploits on their device, or just be responsible and do it against things that you own. Anyways, let's get back to the video. I'd like to take a second to apologize for how long this video took to get out. I've been studying for this certification, and it's kind of got me in a Peruvian necktie at the moment. I will also say, and this is important, so don't skip, Goldfish. This is part of our brand new malware development series, which I know, oh my god, another unfinished series on top of the 300 trillion that you still have to get out there. I know, but you know what? I'm kidding! I made this a standalone video instead of adding this to the process injection techniques, which is going to be the next video in the series, because I don't want to overload you guys with the information you're about to get telepathically beamed into your skulls. And you must understand these concepts first before we start delving into the nasty, gritty ditty stuff, okay? Okay. Processes, threads, handles, what the fuck even is them? Who knows? Who cares? I'm about to learn y'all a thing or two about these here X concepts. Firstly, it's important to mention sooner rather than later that you're going to need some experience with some quote-unquote low-level languages or stuff, because malware development, at least the decent stuff, is all about the super stinky cesspool in which our treacherous CPUs live. So it's important to be somewhat familiar with a language like C, C++, and eventually some assembly. There's also the whole thing about .NET and C# and PowerShell, but gross. First of all, kidding. But that's for future us to worry about. Don't worry, I'll do my best to make this as easy to follow along as I can for everybody. I'm just learning as you guys are. It's like my homework put out so that you guys can learn along with me, okay? And another disclaimer, I am a dumbass. I mean, I'm learning alongside you guys. So if any of this stuff isn't 165.38% correct, don't start foaming at the mouth. Instead, just leave a comment so that all of us as a community, as a team, as a unit, as birds, as corvids, grow as a unit, okay? I care about you guys, and you and me, we're like this. We're a team. Who the fuck is racing outside? Why is it just... You and me, we're a team. We're a duo. You and me, we can do anything. Why? You're going the same goddamn speed as everybody else. I don't understand. Processes. More specifically, processes in the context of Windows. A process is just an instance of an executable. Now, what doth that meaneth in English? Basically, think of it as a container that houses everything needed for a program to run. The executable code, the data, memory, etc. A program or application or whatever you want to call it can have many processes running at once. Moreover, an application like your web browser will spawn a new process for every tab that you create. See? And we can also see some extra information like how much memory... You open a shell and run a command, it'll run as a new process. Some processes can also create their own processes, which are lovingly called child processes. A nuclear family of computer architecture. Oh, another thing, this family is blind. And greedy. So a process typically isn't aware of processes outside of its own existence. To a process, it thinks that it's the only thing running on the computer for the most part. And so if I have process alpha and a process beta, they don't know about each other. Each process has its own virtual address space, or VA space, which it believes is exclusively allocated to it. Meaning, it thinks that all this memory is for it and itself alone. Bastard. Thoroughly rotten bastard. Processes are often seen as being the same thing as programs or applications. However, what you might see as a single application or a program may in fact be a collection of multiple processes working together. Through something like Task Manager that you can find on Windows, we can see that there are three types of processes: application processes, background processes, and Windows processes. Application processes are the processes that are launched to run a specific program. If you open up an application like RAM Be Gone, I mean Chrome, that's an application process. You can see this process spawn in the task manager, and it can be terminated by the user that summoned it for the most part. Background processes. These are the processes that run in the background. They don't require user interaction. They get started automatically, meaning that you do not need to go in and start this one by one. Although you definitely could have a process that starts off as an application or an app process, and then it turns into a background process. These types of processes are responsible for some important system-related tasks, like updating software, scheduling backups, monitoring your system, system, like antiviruses, into indexing files, etc. Windows processes. These are system level processes that are vital for the proper functionality of your Windows operating system. They automatically get launched upon startup and perform critical tasks such as memory management, security, device drivers, and so on and so on. Another thing to remember is the priority that Windows will give a process. In binbos, processes can have a priority level assigned to them, which will determine how much CPU time they're given relative to the other zit-faced nerdy processes, okay? CPU time is just a measure of the amount of time that your CPU spends processing instructions for a specific task or process, okay? There are 6 of these priority ratings, and here they are from the lowest to the highest. The ones to note are real-time, normal, and low, since the other ones are kind of just self-explanatory. If a process has been assigned a low priority, it'll only be given this precious, sweet CPU time when there are no other higher priority processes running. Normal is the default process priority that most applications get, and they're given a fair share of CPU time. Real-time is the highest priority level that a process can be assigned to in Windows. They're given exclusive access to the CPU, okay? They're guaranteed to be executed or be scheduled by the scheduling system of your operating system, which, without getting too far into it, the scheduling system in Windows is responsible for managing the execution of a process and threads on the computer. It decides which threads / processes get access to the CPU and for how long, based on their aforementioned priority levels and some other factors. Highly oversimplified, but maybe in another video. The operating system will give your processes some very useful information, including, but not limited to, a process identifier or PID or PID, the location of the executable file that the process comes from. This is called the image path. Command line, so these are any arguments that have been supplied to this. Lastly, a process gets allocated virtual memory, sure. But a process can also take up CPU time, which means that the more processes you will have running, the slower your computer will objectively be because of all the resources that snotty little infant is using up. And obviously, there's way more to processes and the way that they're prioritized. We haven't even talked about the priority scheduling algorithms or the scheduler itself yet, for that matter, but we'll have to revisit that another time, because for right now, this should be more than enough to get started. A little tangent, if you ever get a super high CPU intensive process and you set that thing to real-time priority, like say for some reason you wanted to play Minecraft on real time for whatever reason, because you have that CPU intensive thing on real time, your other processes, like the things that handle your input and output, like your mouse, your keyboard, everything like that, would lag behind it. Okay, so over here we can see that real-time priority is really dangerous. It's higher priority than nearly everything else. It's higher priority than mouse input, keyboard input, and the disk cache itself. If you foolishly set the priority class of a CPU-intensive program like Minecraft to real-time, it will suck up your entire processor, leaving no cycles for anything else. And over here, if you try setting Minecraft to real-time, your mouse will slow down, the keys take 5 seconds to respond, and Explorer.exe becomes unresponsive. From Mizden, which by the way, we will need to get extremely comfy with because this will be our grimoire, we can read the following about processes, okay? Each process is started with a single thread, which is often called the primary or main thread. But a process could also have multiple threads, just like an application can have multiple processes. These processes may have multiple tiny little threads, which are responsible for different tasks within the process and application. By the way, having multiple threads in a single process is called multi-threading, and it's extremely useful and prevalent in modern applications since it provides responsiveness, better resource utilization, and most importantly, the ability to perform multiple tasks and more. Processes can also create additional threads from any of its threads, and threads and processes are very, very similar. They're both units of execution, kindling that starts the fire that is your program, if you will. However, there are some general differences between these two. First of all, if a thread is a light little feather falling through the sky so elegantly, so gracefully, then a process is a Soviet submarine crashing into the ground at Mach 9. I'm exaggerating a little bit, but threads are lightweight, and processes aren't. Processes consume much more resources. If a process is a team working on a project, then a thread is like a team member with a specific task. Just as each team member has their own role to play in completing the project, each thread has its own specific task to perform within the process. The team can work together to achieve the overall goal, just as threads can work together to execute the program. It takes more time to create a process than it does a thread. It takes longer to kill a process than it does a thread. Believe me, I've tried. Processes are independent of each other. Threads, however, are interdependent and share memory within the process. Just as processes have IDs, handles, or whatever to describe them or interact with them, so too do threads. They've got IDs. They've got handles as well, etc. Great thing about these threads, as we'll see later on, is that just like processes, we can create our own within our script or within our target process to run our own stuff. This is huge for most of the process injection techniques, since we're going to be starting some threads to actually run our code. Next section, handles. Okay, what's a handle? Next section. Okay, actually, we're going to be dealing with handles so much during our time creating malware that I'm confident that if you don't understand what these are right now, through the pure exposure we will have to them while programming, you'll just get the hang of it. Just try to remember that a handle is a generic unit of identification that we can use to represent something. It's like a pointer to our object, and it allows our program or code to interact with it without directly accessing its memory location. Bunch of weird tech stuff, I know, but listen, we're not going to be using these handles by themselves. Instead, we're going to pass them through to some functions that will use them in order to accomplish our goals. There are different types of handles as well, and the most likely ones you'll see when you start experimenting with the Win32 API or the Win API, which we'll take a look at in a second, are handles to processes or handles to modules called handle and H module respectively. There's also handles to windows called HWND. So let's pretend there's a function called, get process info, and it takes a single argument, which is just a handle to the process. Okay, without the valid handle, you won't be able to interact or manipulate the resource. Do you get what I'm saying? Another thing to note is that handles are system-wide, which just means that if we have two processes, A and B, if process A finds out its process handle, window handle, module handle, or whatever, it can send the handle value to process B, which can then do something with it. Not that important for us right now, but it's still good to know. I'm pretty sure like 87% of you are already familiar with what APIs are, or application programming interfaces. But if not, don't worry, I'll explain it anyways. An API, in the simplest way I can describe it, is just a way for something to interact with something else using predefined rules or protocols. For instance, you guys remember that video? That one video by Jarvis Johnson where he ordered a pizza using the pizza site's API. Those functions were created by the developers of that site or that program or whatever, so that you could use it in your code. Otherwise, the code that this person would have had to use would have, number one, been a lot harder to implement or much more work. And number two, may have looked completely different to how it does now. An API makes it super neat and easy to do what you're trying to do with someone else's code because there's functions made specifically for those purposes most of the time. So just like the pizza store, Windows has API for developers to use and for hackers to abuse. I'm so clever. This API is aptly named Windows API or Win32 API. Why 32? Is it only for 32-bit systems? No, it's not only for Windows 32-bit systems. You'll see this a lot with Microsoft, but they love to make sure that their stuff is backwards compatible, and they will love even more to shove it down your throat that it is. Even though modern versions of Windows runs on 64-bit architecture, the name is still kept because of the backwards compatibility. You know, it refers to the fact that the API was designed for 32-bit versions of Windows, like Windows 95, 98, NT, 2000, yada yada. So Win API, or whatever you want to call it, refers to the same thing. That being the API that Windows OS uses for functionality. There's a shit ton of documentation. Okay, let's go give it a visit. Another thing to internalize is the fact that Win32 API is well documented. We'll get into why that's important maybe later in a future video. Since that's documented, the lower level API like NT API from NTDLL is not documented. While Microsoft has given some of its documentation out, but most other things have been reverse engineered by insanely intelligent people. That's just a huge tangent. If that doesn't make sense to you, literally don't worry about it. So let's give the MSDN a visit. So listen, I know how goddamn yucky this looks, but you will come to love this resource. I'm not kidding. You know what? I'll prove it to you. Let's do two examples. The first one, let's do a super easy hello world example with a MessageBox function using the Win API. Okay, so understanding what functions you will need in order to do the thing you're actually trying to do will come with some exposure, experience, maybe some research. It's not really that obvious since there are so many of these functions. I'm sure you can find some that do the same exact thing that you're trying to do with one function. Well, luckily for us, a MessageBox that we're trying to do is literally just a single function, okay? So let's begin by setting up our script. In Visual Code or Studio or whatever IDE you want to use, let's create a new C file. We'll start by including the Windows header, which will let us use all of the Win API. And if we actually go into this header file, we can see what it is. It's just a bunch of includes. So this header file just houses several functions, macros, data types, constants, structures, directives that we can use to interact with the operating system from userland. And userland versus kernel stuff is something we'll get into later. So after including the header, let's set up our main function. This is going to be our script entry or program's entry point, and let's make the main void so that it doesn't take any arguments or return anything. Now, here comes a scary boogeyman, the win API function MessageBox. Let's examine the way this function is set up in the documentation. The first part that we see is int. This part before the function is what the function returns. In this case, the MessageBox function returns an integer value, which this integer value actually means something. It means the value that gets returned will actually tell you what the user picked from the message box. For example, if the message box that gets displayed has an OK button or a no button, and we pick OK, the value that would get returned would be 1, and to denote that we picked OK. A thing you'll notice is the weird naming convention that Microsoft uses, like hprocess or hthread or hmodule. This is actually called the Hungarian notation, which is just when we use some letters or a letter to define a variable type in the variable name. So hprocess is a handle to a process. Hthread is a handle to the thread. You might end up seeing variations of this notation upon your trek studying, like phandle or process handle or handle process. And this, Mr. Peppy, is none of your goddamn business. Just kidding, Peppy. Please don't force me to learn Haskell. Thanks. The point is, you'll see some things when you start tinkering with the API. Some terrible things. So don't get too caught up on it if it all looks a bit different. Just spend some time working on your own scripts and understand the theory of what you're doing rather than remembering the names of the variables and symbols or whatever. And that way, even if you run into someone who's using a totally valid and 100% decipherable naming convention as I do, Peppy, you'll still be able to understand what they're doing. In terms of malware development, however, we actually want to make our enemies' lives as difficult as possible. Okay, so we discovered what the function returns and what type it is, all that stuff. Let's now start moving on to the individual parameters of this function. So we can see that the first parameter is an input and it is optional. From here, this is why I say this is such a good resource, is that all these parameters, they will tell you detailed description of each of them. The first parameter is a handle to the owner window of the message box to be created. If this parameter is null, the message box has no owner window. We're not going to worry about owner windows. We just want a message box to spawn, not attached to anything. Let's start building this. I don't know what the hell that was. Probably a ring 0 rootkit, whatever. Let's start building out this function little by little, okay? A thing that we will come back to is that you'll notice that there's a lot of these variations of the same function. After we get the message box set up, we'll come back to this and go through these one by one and see why there's so many. For now, we're just going to choose message box. See, expands to message box W. W meaning wide char, but again, we will come back to that later. First parameter. First parameter is optional. We don't want to attach any owner window, so we're just going to type in null. The second parameter is also an optional, but we actually do want to include this one because this will be the text of our message box. This is the message to be displayed, and we can add in new lines or carriage returns to really format the message how we like to inside of the box. Now, we're going to figure out what message we're going to put into this message box. We will come back to this again, but for now, we're just going to put an L here as well. Don't worry about it. We will come back to this when we talk about all those different variations of the same function, okay? Next section. This next section is going to be the message box title. And if we specify null here, the default title will be error. This will be the actual title of the message box. Let's fill this out, remembering to include this L. The last parameter is my favorite, and it's just going to be the type of buttons that we want inside of our message box. And we can also make the message box display icons as well. We can see that we can specify any of these. This is why I love the documentation too, is because it will tell you literally right here what it is. And you'll see these values. You can also, in place of these names, just specify these as well, and the same exact thing will happen. These values get expanded to these anyways, but we're going to keep it simple for now. So let's say that we want a typical yes, no, or cancel, that option, and we would include this as our last parameter. So let's do that. Now we could at this point run this and we will get a message box. Actually, let's do that. Make sure to save. Let's start. Sorry. Also make sure you specify W here because it expands out here anyways. And if we don't, then for some reason the A version or the aNEqC version, which again we're going to talk about in a second, gets put. So instead, just do MessageBox W. It's the same thing. Once we press run and compile it, we should see our first MessageBox. See, it was not that bad at all. We could click on any of these buttons and remember what happens when we do. This function returns an integer value that corresponds with the button that we pressed. Okay, and there we go. We just did our first message box. Now, another thing we can add to this are the icons in a message box. So there's all of these, and you can see over here what they look like. In order to add one of these, let's say we want to, we're excited, this is our first message box. Let's say we want the exclamation. What we would do is specify this value like so. And now if we save and compile, we should get a message box with an exclamation icon with our message. Just like we thought, it worked. Now, let me format this a bit better. I'm just doing this for the sake of demonstration, but what were all those weird different variations of the same function? Well, the thing is, these WinAPI functions, some of them have different versions. So W stands for wide char or wide character for Unicode string, which is why we put that L macro in front of our string, just to make sure that it gets encoded as Unicode. As we can see, if we remove those L's, but keep this as a Unicode function or a wide char function, we get this, which is why encoding is very, very important. And now there are several ways we can fix this. A way we could fix this is by using the aNEqC version, right? And that way we wouldn't need to use Unicode encoding because we'd be using aNEqC. And if we save, we'll see that it works just like normal. However, aNEqC is pretty old and dated, so whenever possible, it is best to use Unicode. And if we wanted to use Unicode, we can specify W, which by default will get used in your scripts. I don't know if it's like that for every single IDE, but for Visual Code and Studio, it's like that. We just have to make sure our encoding reflects the function that we're trying to use. And there you go. How about those other functions? So we got W done, we got the A done, but what about the EX? Well, the EX stands for extended. Basically, functions with EX at the end of them just means that function usually gives you more parameters to tinker around with for more tinkerability, more things for you to utilize, or more debugging options or stuff like that. There's a very common one, which we're going to be using for our purposes in process injection called CreateRemoteThread. And CreateRemoteThreadX for extended. Now we can take a look at these two functions and see how they differ. The documentation just lets you search for whatever. And then from the documentation we can see, use the CreateRemoteThreadX function to create a thread that runs in the virtual address space of another process. Optionally specify extended attributes, hence the EX. And if we click on this, we can see there is a little bit of variety. We get a little bit more things to play around with. There are more parameters usually in the extended ones, and that's the main difference. Okay, now that you're a master at the Windows API, you know, you're already dumping the process and thread environment blocks, and you're finding out the kernel offsets and using indirect syscalls to make your code less suspicious. I'm kidding. That first example is just our hello world, but we're going to move into something that's more on the caliber of what we've been talking about. Okay, it's going to incorporate the handles and the processes, and this will be the last example that we do before the video will end, and then we can pick it up in the next video, which will be about the actual process injection techniques like shellcode injection and DLL injection. What we're going to do now as our final thing is to create a process using the Windows API. So we created a message box. Great, fantastic, amazing. But we're going to incorporate all of our learning, crystallize that foundation by making a process. So first, let's find the documentation. I'll tell you right now that, again, it's just a single function that we need to use called CreateProcess. And like MessageBox, there's different encodings. We have the wide function and the aNEqC function. We're just going to use wide. So let's go find that. Okay, we're at the CreateProcess function. And a thing to note is that this function is not the same as OpenProcess. We are literally creating a process here, whereas with OpenProcess, we're just opening a handle to a process that's already existing. When I'm first starting out, I like to copy the syntax of the function and just paste it in my programs. Create a new file, call it whatever you want, with the file created. And like we've been doing this entire time, let's include the Windows header. Let's set up the main function. By the way, it's just expands to 0, so it's literally the same thing as just doing return. 0, but as our code gets bigger and bigger, I really find that it's helpful to use this instead, just for the sake of clarity. Now, let's copy and paste that function, just so I can reference it within my code. Just fix the indents. We can see that this function is a boolean, which allows us to utilize it in a pretty cool way. I'm going to say, if not CreateProcess, then we're going to return an exit failure and let the user know that the process could not be created. We can see this just expands to 1. Any non-zero digit that gets returned upon exit as an exit code usually signifies that there's an error of some sort. You'll see this a lot in Linux. We'll also put in a print statement. We love our status symbols as hackers. So I put in a print statement, and then over here just have it formatted to use the output of the getLastError function. So if we look at the actual documentation for this function, we see that it will just retrieve the calling thread's last error code value, which is maintained on a per thread basis, and it just returns the last thread's error code, right? Which we can then look up to figure out what went wrong. But back to the topic at hand, let's just make this a little bit easier for us to follow. So we can see that the first parameter is the application that we want to run, which in this case is just going to be the path to the executable. Let's just get this function to start up Microsoft Paint, which by default the location of that is in System32.
So that was a fucking lie.
Let's write out the path of the executable. Remember, Unicode, so we make sure to encode properly. Next, this is where we specify any command line parameters. For here, we're not going to do anything, so we'll just do null. This parameter determines whether the return handle to the process can be inherited by child processes. It's not important to us. If we do null, then it means this handle won't be inherited, so we'll just put it as null. It's not really important for us right now. Same thing with the thread attributes. We don't really care for that right now. Do we want to inherit handles, right? You can see the Hungarian notation coming in. We'll set this to false. Really not important for us. Now, this part is important. This is our creation flags. So, do you remember that talk that we had about the process priority? Well, this is where we actually set it for our process that gets created. Usually I would leave this null, or sorry, 0, but because we were talking about those process priorities, I'm going to actually set the process priority for this one. We'll do below normal just as a proof of concept. This next option is a pointer to the environment block for the new process. We don't need this. If we set this to null, the process that we create will use the environment of the calling process. So we'll set this to null. We don't really need this right now. This is just the full path to the current directory for the process. If we set this to null, the process will have the same directory as the calling process. We don't need this either, so let's just set this to null. Okay, for these last two, we actually need to do a little bit of setup here. But we're almost done, I promise. These two parameters require us to set up some structures, which will get populated by this function. If we look at the documentation, which again, the holy grail, right? We can see that this parameter that we were just looking at, second last one, is a pointer to a startup info or startup info extended structure, which if we click on it, is this big structure already created for us. So what we have to do is just use this structure and create a variable for it. Remember that Unicode? You see how it was already populated? We actually have to assign this to a variable, so let's just call this SI for startup info or start info. Now, remember, this is going to be a pointer. This parameter, which is right here, which we're about to fill out, needs to be a pointer to this structure that we've just set up. And we can do that by, and we just have to do the same thing for the process information. If we look at the documentation, look at that, it's already there. So set up the structure, assign it a variable, and use it in our function. And we'll call this PI. Now, if we try to run this, we should see a paint process start up with this priority. Oops. I also forgot to include the header for printf, so just include that. So. The thing is, right, in this debugger, even though it has crashed, which we'll get to, we can see what we would be able to access from the structures that get populated in the process information structure that we've set up. We can see that we would actually get the ability to reference the process ID of this created thing, which we could put into like a format string or something like that. So we also made the change to, well, first of all, not start a paint, but we're going to start up a notepad. And I also initialized these structures. If we run this code, we should see a process start up notepad. And there we go. Notepad has started. So we are like 99% done. So as a final hurrah, let's start interacting with this structure and get some information about this process that we created, about our child, that greedy little infant. Okay, but we want to get the process ID that gets returned, which is stored like this. You see, we get all of these things, so we're just going to get the process ID. So after compiling this, now if we run it, we should see a printf statement as well as our process getting created. Now would you look at that? We can actually verify this by using an amazing tool that I use almost every single day, Process Hacker. And if we search for something like Notepad, or if we just search for this reported PID, there it is. And remember we put it on below normal priority class? We can see that it's set as that. And if we get rid of this line, we can see that it's actually going to be set as a normal priority. So let's get rid of that, set this to 0. Compile, now let's run it. Okay, 32428 is our PID. It is set at normal. Look at that. We did it. Even if you just stuck out to the end of this video, which I know is going to be long, you can probably hear it in my voice, but what your homework will be now is to go out and try this. There's no feeling like it. Seriously, I want you to, number one, first of all, make a message box like this. Make it and interact with different types of encoding and the different functions, the wide functions, the ANSI ones, whatever, the extended ones even if you want to. And then secondly, I want you to create a process. And as an extracurricular, you can also try opening a process that's already existing. I want you to try using open process as well. That's going to be your homework. I sincerely hope you guys enjoyed this video. Again, apologize for how long it took to get out. And I also wanted to thank you guys so much. We just recently hit 1,000 subscribers, which is mind-blowing to me. This is insane. We'll continue off by doing some process injection later, since we now have the groundwork done. That being said, guys, I really appreciate you watching, and I thank you for watching. Until next time, goodbye.